Hey, Physics 30, let's talk about fission and fusion today. So back in the day, Ernest Rutherford, the same guy that discovered the nucleus there, was the first to force an element to change into a different element because he was dealing with alpha particles when he was doing his gold foil experiment. So he was playing around with those, shooting those into other gases and stuff, and noticed that the gases changed property. So it changed from, in this case, you shot into nitrogen gas, and it changed into oxygen gas. And totally different properties because of that. And along came a proton to come with it, and this helped him discover that, yeah, protons were part of the nucleus. So it was just the alpha particle was hitting it, combining, and popping out this extra piece. So you notice that in this, he actually created a pretty good thing of fusion here. He's taken two smaller pieces, slightly smaller pieces, and he's created a larger piece out of it. So this is what we call artificial transmutation. So this is the idea of like changing lead into gold and stuff here by forcing something else by either taking away protons or pushing protons into it. So like I could change mercury into gold by removing a proton, right? Most likely when you do that, you're going to create radioactive gold, but sure, I'll have the properties of gold for a little bit until it decays. That's fine. So this is technically fusion because you're creating a larger piece. Usually when it comes to fusion, you are going to create larger pieces of that, but that's fine. Or maybe it's just hydrogen producing helium, but you are taking two smaller pieces and you're creating this larger piece. Now, everything that we said before regarding radiation and conservation of charge and nucleons holds true, and everything we said before, how we could lose mass to produce energy, also holds true. So we're going to do some more mass defect calculations here. They're a little bit simpler because we're not going to deal with those extra electrons and positrons that beta radiation created for us. But the same kind of calculations that we're going to use. Now, everything holds true. You can see on the bottom here, 7 plus 2 is 9, 8 plus 1 is 9. Everything on the top is the same, so 18 on the left-hand side here, 18 on the right-hand side. So all the nucleons are balanced out here, and all the charge is balanced out on the bottom. In this case, we're just talking about protons. Okay, so just led down to the Manhattan Project, atomic bombs, and a bunch of other stuff here regarding nuclear power. And I'll put some links in the description about what is the dangers of nuclear fission and nuclear fusion, and what are the good things about nuclear fission and fusion. All right. There's a very good animated video on that. I'll give you the link to that so you can watch those videos. Okay, so fission, particularly fission, is the idea of taking something that's large. So a nucleus that usually has an atomic mass of 120 or greater. So we're talking like uranium usually, which is an atomic mass of 238, or taking tin or xenon, cesium, taking those guys and splitting them into two smaller pieces. So fission is the process of taking a big guy and split it into two smaller pieces. Sometimes that just happens spontaneously, right? Maybe just through the process of regular decay, uranium might split into two smaller pieces, but usually it's pushed a little bit. So you take a slow-moving neutron, and you kind of shoot it into the nucleus. So you can see in this little picture here. And by doing that, you kind of disturb the nucleus a little bit. It's kind of was happy the way it was, but when you shoot it in there, it becomes a little bit disturbed, and it splits into two pieces. Now, those two pieces, in this case, barium and I think krypton down here. I can't tell what it is. Oh, here it is, yeah, krypton. Those two pieces, it's kind of random. They're pretty even in this situation. You got okay, maybe not as even as I thought it would be. 56 and a 36, but they could be a few different things. It could be a xenon, as long as the numbers add up there. What they also noticed, that though it wasn't proven at this time here, that it produced more neutrons as well, right? Produced by reaction. You can see here in this picture, a neutron goes in, reaction happens, pops out these two daughter particles, the bigger daughter particles here. So just move my face a little bit smaller. So the daughter particles, and then three new neutrons. And these neutrons or it can continue on just like this neutron was here and hit more atoms, more uranium atoms or more other atoms, and continue the process. And this is what we call a chain reaction. So it produces, for every one of these, it produces 3 neutrons. Those 3 neutrons can produce 3 more reactions. Those 3 more reactions can produce 3 more neutrons each, and then it just exponentially grows. And if there's nothing stopping it, we could have a meltdown, right? So most of the time when we talk about nuclear reactors melting down, this is what's happening, is where you don't have the control of those neutrons, and these just go crazy and just start reacting completely and just releases tons and tons of energy and then just melts the whole reactor down, right? So they introduce these things called control rods and special water and stuff to try to limit the amount of neutrons hitting other uranium atoms. You can't limit the amount that's being released. They just have to be absorbed somewhere else where they can control them. Call them control rods, obviously. Okay. Everything has to hold true, though. Like all the nucleons have to balance out. So you might see something that looks like this, where it says 3 or 1 over 0. So this just says there's 3 neutrons here. So when I add up all the numbers on the top, I get 236. If I add these numbers on the top right now, ignoring the 3, I'm not going to get 236. All right, I'm going to get 1, 2, 3, 4, 5, 6. Right, so I'm going to get my 236 if I include that. There's 3 of these, and all the numbers on the bottom have to add up as well. I suspected at the same time that large quantities of energy were going to be created as well. All right, and it was proven many years later, a couple of years later here, that some energy is released in form of kinetic energy. So all these pieces are being shot off in different directions. We've got kinetic energy, we got gamma energy coming out of this, gamma radiation, because all these energy shells had to restructure themselves to the new energy shells that barium and krypton have. And so we got lots of energy coming out of this. And it just makes sense because that's how an atomic bomb kind of really works, or how nuclear fission works. That energy is then used to heat the water up. The water is then in the form of energy. It's used to turn a turbine, and the turbine produces electricity because that's just the generator effect there. Okay, the amount of energy that we can find from fission is just the same way we found it before. We could find out how much mass was lost in this reaction. I can find out how much energy was by using E is equal to mc squared. Now, a very key thing later on that we're going to talk about in more depth later, when we talk about fusion, we're going to bring this back up. This is pretty key. The amount of energy released per kilogram, per mass, like some people say pound for pound, right? In this case, mass for mass, because pounds are imperial units. We like to keep it metric here. So mass for mass, fission releases 2 million times more energy than coal. Coal is a standard combustion reaction. So when I want to compare reactions together, I'm going to compare just regular combustion reactions, things that react with oxygen, produce water and carbon dioxide. That's a regular combustion reaction. It's going to produce kilojoules of energy per mole. And a mole is a lot of particles. And when we talk about fission, we usually talk about per nucleus. Okay? But a nucleus is just a fraction, it's just one of the particles. A mole is 6.023 times 10 to the 23 particles. Right? That's a considerable amount of particles. If I were to scale up the number I would get from this reaction to 1 kilogram, I'm going to have 2 million times the amount that I would have for 1 kilogram of coal. Okay, so compared pound for pound, mass for mass, fission is way more efficient. The amount of energy released is considerable. So it also just means you need less of it to produce the same amount of energy. Okay, if I wanted to think about that too. You'll probably watch those videos and you'll see that too. They'll talk about that. Okay. Yeah, so the next video, because it's at the 10-minute mark, I can't remember how long these questions are going to take, we'll talk about how do we calculate that? How do we calculate this energy in the uranium reaction? Or into another one here, this one here, the uranium turns into bromine and lanthanum, right? Bromine or bromine? Yeah, I can't never remember how to pronounce it properly. It's the same uranium-234, but split into two different elements, how much energy is released in that reaction. And then what I'm going to do with one of those reactions, doesn't matter which one, I'm going to scale it up to see how does it compare. How much energy, if I had a kilogram of uranium, how much energy would that be? And I'll see you in that video. Bye.